Hello everyone. Welcome to our second webinar. Hello to everyone joining on Zoom. I can see that some of you are raising hands. So we expect to have around 200 participants on Zoom. That's why we disabled audio and video for all the participants, so you can't actually say anything. But if you have any questions on Zoom, you can ask them in a Q&A section. All right, hello to everyone on YouTube. If you want to ask any questions, I'm not going to go through the YouTube chat, so you will have to join the Zoom webinar to ask your question. All right, the sound is good. All right, so I think we are ready to go. So, hi everyone. This is our second webinar, and at this time the topic is artificial intelligence, or AI, and machine learning in Unity. So, AI in general, it's a very broad and popular topic nowadays, especially in games and other industries. Many companies try to embrace AI, and yeah, there are many materials online that you can find about machine learning and AI and different AI subsystems, but I still hope that this webinar is going to be beneficial to you, and you're going to learn some new knowledge about Unity and how you can apply some of these AI algorithms in the Unity editor. Before I start, a few words about me. My name is Marek. I'm a Unity evangelist at Unity Singapore. Before I joined Unity, I worked as a programmer in several companies, mainly as a game or gameplay programmer. But I had a short experience with VR and AR. And every day I work with a very talented group of people called field engineers from Vietnam, Thailand, Malaysia, Singapore, and Australia. And we are working on some very exciting projects for external clients. So if you are a developer from our region, from SEPAC, you might have seen me at some events, especially game or other industry events where Unity was present. You might have seen me there. And privately, I am an AI enthusiast, so I'm very happy to give this talk today because I think it's a very exciting topic. And what's more, last week we released Machine Learning Agents version 1.0, so the timing is really good to talk about machine learning in Unity. And yeah, I hope that this will be beneficial to you. So let me just quickly check if we have any questions in the Q&A. No questions here. All right, so let's take a look what we'll learn today. So as always, I'm going to start with some very basic concepts and slowly work our way to more advanced topics. And today I'm going to start with AI Planner. So this is a preview feature that Unity Labs presented us last year. And this allows you to create some very interesting behaviors in a very different way than it's usually done with state machines or techniques like behavior trees. So this small robot that you see going around in the background, this is a quick demonstration that I created. It's a cleaning robot that's not told deliberately to perform any certain action, but the AI planner is planning actions for him. So we're going to start with that. Next, we are going to move to machine learning agents. I'm going to give you a short introduction to machine learning and reinforcement learning in Unity with this great package, Machine Learning Agents. And we're going to go through one full setup. So we're going to create our own learning environment for the agents. And then I'm going to show you some of the examples that come with the GitHub package that we distribute. And finally, This is more like a bonus section, but this is something I promised you during the last webinar, that I'm going to show you how to bring your pre-trained machine learning models into Unity. And you can do this with this package called Barracuda. It's our inference engine that allows you to bring your pre-trained machine learning models. Here I have a PyTorch model that's trying to recognize some images that I draw on a screen. Topics, as you see, they are very diverse, so we have quite a lot to cover. I was hoping that I can also add some stuff about navigation meshes, nav meshes, but I think this session would be way too long, so I want to wrap everything up in around 1 hour, 20 minutes. So I'm going to skip the navigation meshes today. This is one of the most basic kind of AI systems that you can find in any real-time application. That's why I decided that there are plenty of materials online that you can find, so I'm not going to talk about this topic. This is a non-hands-on session, so I'm going to give you some demonstrations, but if you want to follow on your laptop or your computer, it might be a little bit too fast, because I'm going to switch quite quickly between different applications. And just to make everything go faster and more clear, I pre-recorded some sections, because of course you don't want to look at loading screens and things like that. So yes, this session is going to be recorded, and we're going to put it on YouTube. It should be probably live on YouTube today or tomorrow at the latest. And yes, we have a Q&A section, and after each section about AI Planner, machine learning agents, and inference engine, I'm going to stop and go through the Q&A section and clear everything that you asked me there. All right, so without further ado, let's start with the AI Planner. This is a preview feature. This is something I need to I need to mention here. So it means that it's not ready for production, but it's a very interesting package that our research team in labs at Unity Labs is developing. It's in a very early stage, but I think it's worth to take a look and maybe experiment yourself and see if it works for your project, and hopefully you can give us feedback on forums on what do you think about this feature. But first, let's talk why do we need something like AI Planner or machine learning agents in our application. So this slide, I took it from the Unity Labs, because I think it's really interesting. So there are 3 types of approaches if you want to create behaviors for your NPCs or any kind of AI agents. So the first one is reactive AI, and reactive AI you can call it a scripted AI, because all the actions, everything that's done by the agent is kind of hard-coded by you. And this also applies to things like state machines, behavior trees. They are just a visual way of scripting your behavior. Also things like utility AI, it's a good example of scripted behavior. Next we have deliberative AI. So this is a big step up from the reactive one. And I think the trend for that started with a game called Fear. They implemented the goal-oriented action programming, and this was one of the most impressive and earliest applications of planners in the game AI. So yeah, this approach is very different because we're not hard coding any of the behaviors. We are letting the planner decide what kind of actions our agent needs to take. And then finally we have the machine learning. So machine learning, it's like a totally different way of creating your behaviors, because you're not telling agent what kind of actions does he have to take. It's all done by reinforcement learning and machine learning algorithms. So in other words, you could say that a reactive AI, you could say using this proverb that give a man a fish and you'll feed him for a day. The deliberative AI would be teach a man to fish and you feed him for a lifetime. And this is one I really like. So for the reinforcement learning, you could say, give a man a taste for a fish, and he'll figure out how to get the fish, even if the details change. So I think this quote is very accurate, because with reinforcement learning, we give very simple informations to our agents, but they can figure out on their own, using different algorithms like PPO or SAC, how to perform certain actions and how to solve complex problems. All right, so back to the AI planner. We are starting with AI planner. So just to give you an intuition of what is happening inside the AI planner. So here I have an example of a pathfinding problem. So imagine that our player, our agent, has to go from point A to Z. Okay, and in this situation we have some intermediate nodes here. And algorithms like A star normally would give us information about the intermediate nodes. So it will give us information, hey, if you want to move to point Z, first you need to go to B, then D, and then finally arrive at the point Z. And this also gives us, this intermediate nodes give us information what kind of actions our agents needs to take. So to move from point A to B, we just need to change the location from point A to B. So we could say that when you're in each location, you're in a different state. When you're at the point A, you're in a state where the location is point B, point A, and so on and so on and so on. So this can be generalized to multiple dimensions. So your state doesn't have to be only location. Your state can be actually something like, do you have a weapon? Does your character has a weapon? What's your, if you're a robot, what's your battery status, and so on and so on. So this can be generalized, and so yeah, I think it's really great that we can take this idea from a simple pathfinding and generalize it to solve more complex problems. So before I continue, I want to show you gameplay footage that I recorded last week. It comes from The Legend of Zelda, and this is example of intelligent behavior that I really like. I'm not entirely sure if they use Planner to solve this problem, but I think it's really interesting how these agents, they appear to be intelligent. And they react very well to changing environment. So even though some parameters of the environment changes, they can adapt and act accordingly. So let me quickly analyze this footage. So here I'm kind of sneaking towards this bogoblins. Bogoblins are these red guys. And here I'm just about to throw my weapon. Okay. And what will happen, again, I'm not entirely sure how Nintendo implemented this feature, but what will happen is that when I throw this weapon and it will land next to this enemy, it's going to probably react with some sort of perception system of this agent, and it's going to make him come into alert state. It's going to wake him up. Okay, so let's do this. You can see that this alert state is signified by this big question mark above his head. So what you will see that he has woken up, he's in an alert state, and probably what will happen is that AI system right now is calculating some sort of sequence of actions that are going to be executed. So now this enemy's goal is to harm our character, and the character's name is Link. So the Bogoblin's main goal now is to damage our character. So he needs to perform some sort of actions to fulfill the prerequisites. So the prerequisites to attack Link are to be in a close melee range and have his weapon equipped, right? But his initial state is he's very far away, so the location is totally different. He doesn't have any weapon at the moment. So right now, probably some sort of planning system is trying to figure out all the possible actions that he can take. Probably move to the location, I don't know, scratch your head, go to sleep, whatever the action is. But what you'll see that the agent is doing, he's performing action move to the weapon. And he's doing this because the next state after that is going to be him being at the weapon location with no weapon. Then he's probably going to execute action, grab the weapon. Then after he grabs the weapon, his state is at the weapon location with the weapon equipped. Then he will move towards the link, and finally his state will be in the melee range with equipped weapon, and he can finally attack our character. So let's take a look. Alright, so this is exactly what happened. Let's take a look again. You can see that he just went towards this weapon, he grabbed it, and he came running towards Link. Now, here it's a very similar situation, so although I didn't throw any weapon next to this second enemy, but here on the bottom right corner you can see that there's this waveform, and it indicates that I'm making a lot of noise. So probably probably a perception system is going to wake up the second character, and he's going to perform the same sequence of actions. Alright, and when I was recording this footage, I just couldn't stop myself and not showing you this. So if you played Breath of the Wild, you probably know these guys. They are like goblins, but they are skeletons. So here when you hit any of them, they kind of collapse and the body is disassembled. And here again, the main goal is to attack our character, to give us damage and to harm Link. Okay, so right now you can see that his body is totally disassembled. And what he has to do, right, to attack us, he needs to hold a weapon. But to hold a weapon, he needs to have kind of his head on his neck. Right now his head is in a totally different place. And to put his head back on his neck, he needs to have both arms. So he's going to find the sequence of actions that's going to let him to basically deal damage to Link. So let's take a look. Yeah, and this is exactly what happened. And once you know how it works, you'll be able to create this kind of behaviors using AI Planner. So now let me switch back to my slides here. And with AI Planner, we're going to operate on 4 simple objects. The first one is going to be trait. So traits, they are like data representing state of your game and of your character. And then we'll have actions, just like with grab weapon, move to location. Yeah, this kind of very simple actions that change the state or change the parameters of the trait. Then we'll have some termination criteria. I'm going to talk about those later. And we're going to have plan definition. Plan definition is something that's going to grab together all the actions, termination criteria, and try to figure out the best plan to maximize the reward. Because in AI Planner developed by Unity, we can give positive or negative reward to each action performed by the agent. So here you can see that there's this robot that I show you at the beginning of my presentation. And what you can see here is that there's some dirt patches scattered around the room, and the robot is going from one patch of dirt to another, and he's cleaning it, he's collecting it, and when his battery level is low, he's going back to the charging station to recharge his battery. Okay, so I'm going to show you how we can implement it from scratch using the AI Planner. So here is my very simple scene, and you can see that I have here this dirt game object with multiple instances of this game object. I have my robot with a nav mesh agent on it. So nav mesh agent is a component that allows him to move around the scene. Then I also have the navigation mesh itself to allow him to move around the scene freely. The robot also has this script on it called the vacuum robot, and it's a very simple C# script. You can see that it has some additional using Unity-ANZSEA and Planner controller. At the beginning of the script, I'm going to grab references to the controller and to the navmesh agent. So this is something I do in the start. So I just grab references to these two components, and in the update, I'm manually updating my controller. So maybe it's not clear at the moment, but this is a very simple C# script, and the only thing it does right now is to update the controller. And this controller, this decision controller, it's something that's holding our plan, and it's basically scheduling and executing our plan. All right, so here I'm going to add some traits to represent state of my this dirt patches and robot. So here in the AI folder, I'm going to right click and go to create AI traits, and name this one robot, and the second one is going to be named dirt. Okay, and now I'm going to, these dirt patches are prefab, so I'm just going to open one, and I'm going to add a component that's going to assign this trait. It's a trait component. This is going to assign this trait and associate it with this game object. So I'll need dirt, and there are a few that come already with the AI planner, the location and movable. They're going to be needed to perform the moving action. So right now dirt has a location trait, so we can identify the location of this dirt patch. And for the robot, we are going to do the similar thing. We're going to give it a robot trait, location, and movable. So right now, our robot will be able to move around the scene and navigate the environment. Okay, next I'm going to add this decision controller. So on the robot, I'm going to add a new component and look for the decision controller. So this is this thing that I told you before that's going to schedule and execute the plan. Right now the plan field is empty, so I'll need to create a new plan. I'm going to right click here, go to create AI and plan definition. So this is going to be just very simple. I'm going to name it move around. And the only action that this plan is going to be performing is navigating between different points. So I'm going to add this this navigate action, and I'm going to assign this plan into my decision controller. Okay, I'm going to remove the auto update because the update is going to happen in my script. And yeah, so this plan has only navigate action, and this is the one that comes with the AI planner package itself. So with this one assigned, I'm going to give it a name of the function that's going to be called when we want to execute this action. So here on an action callback, I'm going to select my vacuum robot, navigate to destination. So this is a way of telling our agent that we have to move to that place. And this is the method itself. You can see that it's IEnumerator, and it's having the reference to the destination game object as a parameter. So here we just grab the position, we display some debug log, we set our navmesh agent destination, and after we arrive, we return. All right, so if I press play, what should happen here is that he should move from one place to the other. Right now, this plan doesn't make any sense because the only action that he's taking is moving from one place to another. But we are going to add on top of that and make it more complicated. Here we can see I start this plan visualizer. So this is something that comes with with the package. And you can see that it's like a tree, and each node in a tree has information about the current state. So right now the current state has the robot position, location, as well as all the dirt patches that exist in the scene. Alright, now I'm going to add a new action, and this action is going to be the one that's going to collect things from the floor, so I'm going to name it collect, and it will need some parameters here. So the first one is going to be a robot, because I want to know the current position of the robot, so I'm selecting robot and location. Next I want to know the position of the dirt, so I'm going to grab dirt and the dirt trait and the location trait, and the precondition to clean it is to have our robot at the position of this dirt patch. So I'm going to say robot location position, if it's equal to dirt location position, then I can actually perform this action. Here we can specify some effects. If you want to create a new object, this is the right place to do it. If we want to modify the object, we can do this right here. We actually want to remove the dirt patch after it's cleaned. So here I'm going to select the parameter dirt as removed, and we're going to give our agent a reward. So every time he collects this dirt patch, we're going to give it a reward 10 to encourage him to perform this action. Let me quickly go to Visual Studio, and I'm going to add a new method that's going to perform collection. So here I'll pass the reference to the game object, and I'm going to destroy this game object after it's collected. So it's super simple. And next one is going to be adding battery to my robot. So I don't want him to collect all the points at the same time. So first I want to add the battery life to my robot to know when this robot should charge his battery. So here on the robot trait, I just added a new field. This is integer with a default value of 100. And you can see that it appears here on my trait component for the robot. And now with this move around, we have navigate, right? I'm going to grab it and make a copy of this navigate action and create my own version of that. So here in this copy, I'm going to rename it to navigate_n. And every time I move, I want to add a new effect. So if I move my robot, I'm going to modify the battery trait parameter. So here, every time I move, every time I move from location A to B, I'm going to do -=10 to my battery. So now every time I move from point A to B, it's going to, here I need to reassign my navigation action. With AI Planner, sometimes you need to click their AI and regenerate the assembly files. So this is what I did there. Now when I press play, you can see that the action was performed correctly, but I still need to assign the method that's going to be called when I actually navigate to the new position. So this is what I did here. And now when I execute the plan, you can see that he's moving from the point A to B, just like before. And yeah, so now I also want to add the collect action so he can actually collect these dirt patches. So here I'm going to assign this collect method that I showed you in Visual Studio to give it a reference to the dirt. So now hopefully what should happen is that the robot is going to move from point A to B. He's going to collect all these dirt patches, and his battery life should also decrease. So here, take a look at the state. The battery life is 90, After the next move it's 80, and so on and so on. So here this is working fine. Next, I think it's the right moment to do a new state termination. So if we run out of battery, we are not going to execute plan anymore. So let's create a new state termination out of battery. And here we are going to check in the parameters, look for the robot and the robot trait. And the criteria is going to be if my robot battery is equal, or maybe less or equal to 0, then we are going to stop executing the plan because robot is out of battery. There is no need to execute the plan anymore. I gave it a high negative reward, a big penalty to discourage this kind of termination state. Okay, in my plan, in my plan move around, I'm going to actually rename it to clean because right now I have collect and move around. I'm going to assign a new termination, this out of battery. This works fine here. I'm also going to give the initial battery life to 30, just to see if it really stops executing the plan if the battery goes to 0. So here you can see that he already collected 1/3 patch. Right now the battery life is 10, and depending on his actions he's actually going to reach the end state, and you can see that the end state has the battery 0, so it means that it's not going to plan beyond that point because there is no point in doing that because he doesn't have battery, and just there's no point in executing the plan and scheduling actions any further. Alright, now I'm going to add a charging action. So I'm going to actually allow him to recharge his battery. So I'm going to add a new action definition, charge battery. And the parameters here are going to be my robot and robot trait, and the precondition is going to be my robot battery has to be less or equal to 90, so I don't overcharge him above 100. And the modification is going to be that the robot battery is going to be plus equal 10. Alright, and I'm going to add it into my actions here, so now he's actually able to charge his battery. And I'm going to give it a game object for the charging station. So this is just an empty game object. I'm going to create a new trait for this charging station. So I'm going to create a new trait charging station. It doesn't have any fields. I'm just going to add a new game object, the trait component, and select the charging station here together with the location, because we want our robot to know where this charging station is located at. And also a very simple script that's going to basically give the robot indication on what's the charging time. So this is a nice way of telling him how long he should wait at this location. You can see here's my charging function, and the only thing it does really is waiting for this amount of time that he needs to. So he's first checking what's the battery level, and then it's waiting the fraction of this charging time. So here I'm just going to create a very quick visualizer for this charging station so we can clearly see where it's located in the scene. So in my example here, it's just going to be a cube. And I'm going to rename it to visual, because it's just the visual part of the charging station. All right, and in my charge battery, I want to add a new precondition. So our robot needs to be at the location. So I need to add a location trait. And I also need to add a new parameter, charging station, to know its location. It's going to be charging station and location traits. And the precondition here is that my robot location has to be equal to my charging station location. All right. So now we have everything assigned here in our plan. I'm going to press play. And hopefully what should happen is that after he runs out of battery, yeah, he goes to the charging station. So this is working fine. And he's going to charge the battery. You can see that he clearly prefers to stay at the charging station. So this is something we probably should discourage a little bit more. Oh, there's a missing argument here. Let me just quickly assign it. So this is a function that's going to be called when we are charging the battery, when we are executing that action. So you can see that he collected one dirt and he goes to the charging station to collect some, recover some battery. And you can clearly see that he really likes to recharge the battery quite often, because we don't really discourage this behavior. So what we could actually do is this is the charging station. Let me just quickly modify one more thing, because right now this charging happened really quickly. I'm going to set the initial battery status here to 0. I'm going to share this code with you later so you can see how it all works together. But now he should actually spend more time at the charging station. So now when he goes to the charging station, he should stay there for 5 seconds. And on top of that, I think I'm going to give him a small negative reward for charging. So when we were collecting these dirt patches, we are giving him quite a big positive reward of 10. So we can see that he's going back to the charging station again. So next thing, I'm going to give him minus 10 for charging, just to discourage this behavior. I'm also going to give him a positive termination definition. It's going to be something like a clean room, so all the dirt patches were collected. So this clean room state termination here. I'm going to give our robot a new integer, so it's going to be counting for the number of dirt patches that are still in the scene. Right now it's hard-coded to 7. I should actually make it more dynamic, but right now it's hard-coded to 7, and every time I'm collecting this dirt patch, I'm going to decrease this integer here. So this positive termination is going to be my robot, and I'm going to in the criteria, I'm going to check the robot and check the cleanliness, and if it's 0, it means that all the dirt patches were cleaned. Then we want to give him a big positive reward. I also want to check if my battery is greater than 0. So here, if I still have battery and the room is clean, then I'm going to give him a big positive reward, something like 1000. Okay, I'm going to regenerate the assemblies. So we're working with AA Planner. This is something you need to do every once in a while. You need to regenerate the assemblies. And I'm going to press play. And you can see that here he collected 1 patch. He's going to the charging station. And after charging for a few cycles, he's going to come back to collating all these dirt patches. All right. So you can see now his preferred action is to collect all these patches, and with every collection, this cleanliness integer is going to decrease by 1 to indicate how many dirt patches we have left in a scene. All right, so that's pretty much it for the planner. I'm going to share this project with you that has this nice battery indicator and a little bit more code, so later you can check it out and see how it works on your machine, on your laptop. So these are some useful links if you want to start trying the AA Planner. I think the first place you should go and see is the Unity forums. So I mentioned that AA Planner is a preview feature. So it means that the APIs might change quite often, and this feature is still in the development. So I think forum is the best place to kind of look for help and try to get some information, because you're going to get replies from people who work on this feature, from developers, from the team that's developing it. And also, if you are interested in the demo that I showed you today, this is this bit.ly link below, AA Planner. So this is a GitHub repository that has all those different pieces that I created today during the webinar. And I think it's the right time to go through the Q&A section. So are TensorFlow 2 and PyTorch now supported in ML agents? So I'm going to answer that one later. How much storage does Unity take up? I want to install on my new computer. So I'm not entirely sure, but I think it should be roughly 1 gigabyte. There are some requirements on our website, so you can check that on the website. This is Unity 2019.3.11. So I always try to use the latest and greatest Unity. Is it available on 18.4? I'm not sure about that. So the thing is that AA Planner inside it uses entities and dots, and the plan execution and everything you saw is actually using ECS pattern. So I think it heavily relies on the compatibility with ECS. So I'm not sure if it's going to work with 2018.4. Can we edit the algorithm behind the AA Planner? So I think this is a great question. One thing that you can do, and this is something that's described in the landing page for the feature, you can modify the heuristic for the algorithm, right? So the heuristic, for example, for A star path finding would be distance to the next location, right? But your heuristics might be totally different, right? That's why we enabled here this API that's going to let you to modify the heuristics. The search algorithm itself, I think it's fixed. So you can't change that, but you can change the heuristics that go into the algorithm. can we use a neural network model to run it? So actually, maybe you could use like a combined solution. Maybe you could train a machine learning model and use it in your heuristic. But if you're using, if you're looking for the pure machine learning approach, I think machine learning agent is going to be better. So the next section is going to be. All right. So Brett is saying that the link is not working. It might be that it's set to private. So I'm going to. I was working on that yesterday still. So I'm going to make it public. So after the webinar, you can use the link. All right. So next, this is going to be very exciting, and machine learning. So in machine learning and reinforcement learning, you don't tell the agent exactly what he has to do. Okay, and this is just like training a pet or a dog. So you can't tell him, like let's say, hey dog, bring me a newspaper. You just can't do this because obviously he can't understand English. And it's the same with reinforcement learning. You can give him some demonstrations and provide rewards if he performs the desired action, or you can provide negative rewards or penalties if he performs some undesired actions. So this is exactly what reinforcement learning does. And here I have a very simple diagram that shows what is happening when we are training our machine learning agents inside Unity. So we have this agent that, based on observations of the world, he can perform some actions that will perform some interactions with the environment, maybe slightly change the state of the environment, and then provide details about how the environment changed together with the positive or negative reward. So we're going to iterate inside this loop. And just to give you an overview of how this is orchestrated inside Unity. So on the base level, we have Academy that's orchestrating the behavior of different brains, and we can have three types of brain. One is going to be internal. So if you already trained your machine learning model, you can use this internal brain with inference engine to drive behavior of one or multiple agents. You can have a heuristic brain. So this is the one that you as a user can give some demonstrations. And also external brains. These are the brains that are used for training the machine learning agents. And of course, this is not so obvious, but underneath all of that, we have the Python TensorFlow environment. And this is why we need to install the Python environment. The installation is pretty straightforward. I'm not going to go through this now, but if you go to our GitHub, you can see that there's a very detailed guideline for Windows, Mac, I think for Linux too, together with information how we can install the virtual environment, and all of that. It's really needed to run this Python TensorFlow backend. All right, so I'm going to walk you through the entire setup from start to finish, how to create this hovering helicopter agent. So this is a very simple rigid body setup, and the only action this agent can take is to give him kind of a thrust, kind of an upward force that's going to push him up. And the training episode ends when he touches the ground. And the positive reward, so the behavior that we want to encourage, is when he is close to a target that's a little bit above the ground. All right, so here in my scene, I have this helicopter guy. Right now, it's just a rigid body with this small propeller on his head, and the only thing the propeller does, it doesn't do any math. It's just rotating the visual. So yeah, it's just a rigid body. Let me just fix the position of that. I'm going to add the floor. So here I'm going to create empty game object helicopter setup. This is going to hold all different pieces required for completing the training episode. I'm going to add a plane. So the plane is going to be my ground. Let's give it a better material because this white is not very visible. So I'm going to add this gridded material and add my helicopter to the helicopter setup. Move it a little bit up. All right, so now when I press play, he should basically fall on the ground, and that's it. Okay, so to create and train machine learning agents in Unity, you need to use some C# scripting. That's why I'm going to show you this slide here. So we will derive a new class based on Unity ML agent, and we need to override 4 methods. On episode begin, so when we begin the training episode, we need to reset the position of our robot. We need to collect observations. We need to perform some actions, and we need to provide heuristic. So heuristic is going to be useful if we want to control ourselves, the behavior of the agent with our keyboard. So back here, I'm going to create a new script, helicopter agent. All right, and here I'm going to remove this part here. Just keep the Unity engine, the Unity engine dot AI. Oh. This was Unity.ml agents. Yeah, this is the namespace I need. I also need ml agents.sensors. So this is going to be used to collect observations. Also, my agent is going to require the rigid body. This is just to make sure that we have it. It's going to derive from the agent class. And here I'm going to add some parameters. So first, public transform. This is going to be reference to my target to know whether or not we are far or close to the target position. I'm going to remove the update. I don't need it anymore. I don't need these comments. I will also need a reference to my rigid body. So here I create the field rigid body. I will also need a reference to that. So in my start, I'm going to say rigid body equals to get component rigid body. Once I have this, I can start overriding my methods. So first, public override, and it's going to be a on episode begin. So this is a place where I reset my agent. Okay, reset everything and create a new training learning episode. And I'll need one more variable. This is going to be my initial starting position. So here on start, I'm going to record whatever my rigid body position was when I started, and I'm going to set my rigid body position here at the beginning of my episode to the start position, and I'm going to set the velocity to 0 and angular velocity to 0 to make sure that it's not moving anywhere. Next, we need to override one more method. This is public override collect observations. This is why we needed to include this sensor namespace. So here I'm going to say sensor add observation, and we want to know the position of my rigid body. So this is going to be a float parameter, rigid body dot position dot y, because we're interested only in y position. We don't need x or z. Then we're going to add new observation, rigid body, the difference between target position and the current position to know how far off are we from the target. And again, we just need the Y value. And finally we need a sensor that add observation, rigid body, velocity, because we want our agent to know how fast he's moving in the Y direction. So this collect observation, you can think of it as eyes of your machine learning agent. This is everything that he sees. Right now we just give it simple float values, but you could add some very complex stuff, like for example camera feed. So you can actually input low resolution image from your Unity camera to be part of the observations for the agent. So here on actions received, this is a place where you want to perform actions based on what you get in the input. So here I'm going to add a force to my rigid body, vector up times my vector action. This is only one-dimensional vector. And because we want to keep everything normalized from 0 to 1, I'm going to add this force multiplier to make sure that we can actually lift this character with values between 0 and 1. So I'm going to set it to here and multiply my force by force multiplier. And here I'm going to record the parameter that's going to tell me what's the actual distance between target and me. So target minus target position minus rigid body position dot y. All right. Next, this is also a place where we want to give some rewards. I'm going to also get the absolute version of this distance. So this is math f abs distance, and here I'm going to check if the distance is bigger than some very high value. Maybe if it's greater than 3. So if we are very far away from the target, then we are going to end the learning episode. So here I just say end episode and return to not continue execution of this method. But if I'm quite close to the target, if my distance is less than let's say 1, then I'm going to add a reward, and my reward is 1 minus distance times some small value like 0.1. And you want to make sure that you keep this one small. All right, and here on collision enter, so if we collide with anything, we want to check if the collider that we collided with, if it has tag floor, ground. So if we hit the ground, then we want to terminate and we want to stop the learning episode. All right, so this looks good. And finally, we need to add some heuristics just to make sure that we can actually perform these actions on my on the keyboard. We want to make sure that the task that we give to our agent is actually achievable by a human, because we might be that we code something impossible to complete for our agent. So here I just give my actions 0, the input from my vertical keyboard. All right, so back in my scene, on my agent, I'm going to add some components to it. The first one is going to be, of course, helicopter agent. I'm going to give a proper behavior name to it. This one is very important because we are going to use it later helicopter. This is my behavior name. This is going to be used in a configuration file, so make sure that you get this name right. Let me close this one here. And the space type is going to be continuous. And we just provide one input, so its value is set to 1. The observation vector is free because we were passing the position, relative position, and the velocity. Next, we need to provide the target game object, so our agent knows where is the target that we want to be close to. So I'm going to move this game object a little bit above the agent here. Move away the directional light so we don't see that gizmo. And so the target is here above our helicopter guy. This is the configuration file that I mentioned before, and sorry, let me just quickly close this one here. So this configuration file, I put it inside my machine learning installation folder, and you can see that there are some parameters here, like what kind of training algorithm do we use, what's our buffer size. This configuration YAML file is a place where you can tweak all your training hyperparameters, maximum number of steps, number of epochs, do we use a recurrent version, do we add extrinsic reward, and so on and so on. So this file looks all right. I'm going to set my behavior type on the agent for the heuristic for now, and see if I can actually control this helicopter by hand. So now when I press my up key on the keyboard, I can add some velocity to it. So this looks great, and I think it's the right time to start the actual training. So to start the training, first I'm going to see if this one is okay. My agent, helicopter parameter, they need to match, so make sure that it's not the name of the file, it's the name of actual parameter. I'm going to switch it to the default, the behavior type, so that the Python environment can control it. And this is just a simple command, ml agent learn. We pass the configuration file, and that's it. We just need to come back to Unity, press play, and now the Python environment takes over control over your agent. So here I speed up the video a little bit so you can see how it behaves after many episodes, and you can see that clearly I made my mistake somewhere, because it doesn't look like it's learning anything even after, how many steps do I have now? I have 12,000 steps, 24,000, and still the mean reward is 0, so it's not looking great. So the thing I'll do here is I'm going to turn this helicopter setup into a prefab, and I'm going to copy it over and over to have multiple agents providing data for my training algorithm. So I'm going to copy it over and over to around 18. All right, so I have now 18 agents, and now I'm going to run all of them at the same time. So they're going to provide much more information to my reinforcement learning algorithm. So I'm going to run it again. Again, this is just a simple command in your Python environment. I'm going to run it in the editor. And right now you can see that they started exactly the same as before. So they are hitting the ground. The behavior appears to be random. and something really funny will happen, and this is related to an error that I made in my code. So if you just give it a few more seconds, you can see that there is some reward now. These agents, they start to get some very small reward, and you can see that they start to figure out that they get more reward when they are above the ground. So some of them, they will start just to shoot in the ground and never come back. So this is related to an error that I did in my code, and the agent is just exploiting this error that I did. And as long as he can get the positive reward, he's going to exploit this behavior, because why not? All right, so I'll go back to my code. And here the distance, right? I'll checking if the distance is greater than 3, but actually what I should be checking if my absolute distance is greater than 3, then I need to restart my my training. Sorry, end the episode and reset the agent. So let's see if this one helps. All right, so again, at the beginning of the training, the behavior appears to be very random, but after what do you have now, 84,000 steps, they start to get some small reward, and hopefully by the end of the training they should be able to stay above the ground. $150,000 episodes. Sorry, steps. 150,000 steps, 168,000, and they start to shoot above the ground, but we are resetting it to come back to the initial position. And you can see that in the console that the mean reward right now it's 0.3. So we are looking for this reward to increase. The higher the reward, it means that we give more positive rewards in our script. So after some time, you can see that here I have now 58. The mean reward is 58, so they're actually able to stay for quite some time above the ground. But what I'm still not very happy is that it took it quite some time. So I had 400. It took it 400 seconds to learn just this very simple task. So there are some more errors in my implementation, and probably some hyperparameters that control my training, they could be tuned as well. So with machine learning agents, your development process is very iterative. So you are going to make errors, you are going to try to tweak your parameters, you try to modify your code here and there. So be prepared for that. This is what many machine learning applications and the development looks like. So here, back in my code, I actually realized that I don't need the absolute position. I only need the relative position and velocity. So I'm going to remove this observation. And back in my Unity, I also need to modify the agent itself to set the space size to 2, because right now we provide only 2 observations. I'm going to stack some vectors together, so we basically provide multiple states at the same time before we perform the training on the neural network. The decision period, I don't think it really matters here that much. And I'm back in my configuration file for the helicopter. I think the training was a little bit slow, so I'm going to try to increase the learning rate by 3. So right now it's 0.001. So what I hope to achieve is with the higher learning rate, my agents can learn faster how to stay above the ground. Okay, so this is good here. I'm going to press play. And yeah, it starts exactly the same, but you can see that they start to jump much faster. So it means that they learn quicker. But you also have to be careful to not overdo with the learning rate. Also, I think to notice that by default, the learning rate decreases with time. So after some time, the learning rate is going to drop closer and closer to 0. So here, after we almost finished training, and you can see that they can stay above the ground for a very long time. At the end, they can stay above the ground almost forever. All right. I also think that maybe adding a small negative reward when they hit the ground, maybe this could also speed up learning a little bit. So this is what I did here. I think 10 is a little bit too big, so I'm going to adjust to 10. Let's set it to -1. I think -1 is going to be the small negative reward, the small penalty that the agent is going to get when it hits the ground. So what I hope to achieve is that it will speed up the learning process. So if I go back to my console here, I rerun it with the parameter 2. This is just a name for the run for our training. So hopefully what I try to see here is that agents will learn much quicker, that they shouldn't hit the ground. And you can see that they do learn quicker. And I'm going to check. This is a tensor board. So right now we allow you to connect your training environment with the tensor board. So here what I do, I compare these two runs against each other. This first one, it was my first attempt. It didn't really work, the blue line. The red line was my second attempt. And you can see that this mean reward, together with all different training results, is being passed to this tensor board. The blue line above there was my newest training, so you can see that it shoots higher much quicker. So this blue line, it's my new training that I do now. So it's generally performing better with this small negative reward. I actually did one more error in my code. So when I give it a reward based on the position, I should actually give it a absolute distance from my target. Right now I'm giving him only a distance to my target, so this also affects my behavior. So I should modify that later. All right, and after you train this, after you train your model, you can go right into your machine learning installation path, and you can grab the model. It's going to output the model automatically, and you can assign it to your agent here at the model. And you can also set if you want to use the inference engine on a CPU or on a GPU. Of course, if you have compute shaders supported on your platform, the GPU is going to be much faster. So here you can see the final result. My very simple helicopter agent hovering above the ground without any help from the player. So I hope this gave you an overview how do we work in machine learning. As you saw, it's a very highly iterative process. You are going to make some mistakes and errors, and I think half of the success is providing the right observations to your agent, and also knowing how to tune your hyperparameters. We do provide some examples on GitHub. We do provide some examples on GitHub, and I want to show you a few of them. So the first one I really like is the curriculum learning. So on the video at the bottom of the screen you can see the agent. His goal is to go and touch the green button, but the problem is not so trivial because this wall is very high. He first needs to jump over the wall, but again the wall is too high to do that, so he needs to perform sequence of actions. He first needs to push the block against the wall, jump on the block, and then jump over the wall. If you start right away with this approach, it's going to be almost impossible for your agent to figure out on its own how to do that. What you can actually do is to set up curriculum learning, where you will start with very simple case like the one here. So you can see that we are having no wall here. After some time, when our agent learns that he actually has to get close to the green button, we can add a little bit more difficulty to that. So maybe add a small wall and then a little bit higher and higher and higher to kind of speed up the learning process. Because as I said, if you start with this hardest example at the beginning, it's going to be almost impossible for your agent to learn it right away. The second thing I want to talk is the multi-agent soccer training. So this is a football game, and what we did, we set up first agent, the first brain, to train and be offensive player. So he's always next to the opponent's goal and he tries to score. Then we train a second brain to be a goalie and protect the goal of your own team. After you train these two brains, you can actually let them play together against each other, and you can use it as a training environment. So you can actually let this goalie and the offensive player to play against each other, and they will try to figure out the best and more optimal way to score goals. This is an example of how it looks like after the training. Another example. So this one is a little bit more sophisticated because it requires some memory in your agent. So here at first, our agent, he has some ray casts that he casts in front of him to detect what kind of object he sees. So here at first he rotates towards one of these two green buttons and he sees X or a circle. If he passed over this first block that tells him which one he should hit, he doesn't see anymore. He has to remember himself what is the right choice based on what he saw before. So to achieve that, we use something called the recurrent neural networks to give him some memory, so he can remember observations from previous steps. Next, this is a very funny looking spider, and this is the behavior was fully trained in Unity using machine learning agents. So he is getting reward when he's getting closer to this green target, and the only actions that he can take are torques and forces that we can add to joints of this spider. He's like a ragdoll. He's based on, he has 4 legs, 8 joints. So we basically just have 8 dimensional action vector that's giving torque to these joints, and he figured out on himself based on this reward that he needs to apply a certain force to certain joints to move closer to the target. So this is very interesting. And something I think looks really funny is this guy. So it's a very similar scenario. Again, we have ragdoll, and it's controlled by physics. It's fully based on physics, and we give him a reward, very very small reward every time he stays above the ground. And when he moves closer to the target, we also give him a little bit greater reward. And when he hits the ground, we give him a negative reward. This is something that we shown, I think it was 2 years ago. Right, it was one of the first features that we implemented with machine learning agents, it's imitation learning. So here on the left you can see we have a human player, on the right we have the AI player, and the AI player is basically taking the recorded instructions of the human player, and after a while, based on demonstrations, he can recreate very nicely the human behavior. So after 5 minutes of training, it's basically as good as a human player. So these demonstrations, this is something that you can try yourself. And you know, for example, the helicopter example from the beginning, I think this helicopter had superhuman abilities, because I wouldn't be able to control it to stay above the ground for more than 3 seconds, but he was able to stay above the ground almost infinitely. So this was a superhuman behavior, but with imitation learning, you can actually create behavior that's very close to human, and you could train your agent maybe for 30 seconds to make like very, very easy AI opponent, and maybe after 3 minutes it will be like average opponent, and after 10 minutes this will be expert based on the human expert. And also you could give maybe different personality to your agents if you provide demonstrations from different kind of players. So it's a very, very interesting concept. And here are some useful links that you can check out if you want to learn more about machine learning agents. There's a landing page and the GitHub for the main repository with documentation and manual. I'm going to launch the Q&A section to see if you have any questions. Are these AI built-in components available for mobile and XR? So yes, you can use the models in your mobile device using the Inference engine. It will run on a CPU. It should be fine on almost any device, but if your device supports the compute shaders, you can run your models on a GPU. But of course, you can't train your agents on a mobile device. This is not possible. What versions of TensorFlow are supported? What about PyTorch? As far as I know, I think this environment that we create, I'm not sure which version of TensorFlow it's using. Is the code for the imitation learning available? So there was a blog post, I think 1 year ago on Unity website. I'm going to share a link with you. If you go to Discord channel, we can bring the discussion to the Discord, and I can give you all the links you want. Why the video is not smooth? Sorry to ask. It could be my internet. Sorry about this. So what if we give the huge reward? So the problem with the huge reward could be that we could overfit for this one particular scenario. So there was a question about details for the sensor observations for the machine learning agent. So we give this positive reward for him staying above the ground to make sure that our agent has a feedback on that what he's doing is something that we desire. So the only way to communicate with our agent and affect his behavior is by giving him positive and negative rewards. So every time we want to encourage behavior, we give it a positive reward. If you want to discourage behavior, we give it a negative reward. Yes, the video is going to be uploaded to YouTube after the webinar. TensorFlow, it's basically a Python environment created by Google that has this kind of SDK for machine learning. It's very, very powerful. All right. Let me move to the last section, which is going to be about the inference engine, which we call Barracuda. So Barracuda, it's a package available in the package manager. It's still in a preview, but this is something you definitely can try and see if it works in your project. And this supports TensorFlow models, so you can convert your TensorFlow model using our script to import this into Unity and basically evaluate your machine learning model in Unity editor. It supports Onyx models, so the demonstrations I'm going to show you later are going to be based on a PyTorch model that I exported to Onyx. Onyx is like an open format for machine learning models, and it's multi-platform, so it supports Linux 64 bits, Mac OS, Windows, iOS, and Android. And basically the inference on CPU, so your models being evaluated on a CPU, should work on every platform. And also, if your platform supports compute shaders, it should work on a GPU side too. So the typical workflow here is that we load the Onyx file to your project. We load the model from the asset using the script. We create the worker, which is our inference engine. We execute the model and fetch the results. So this is something I'm going to show you here. I created a simple model to learn to play the quick draw. So quick draw is this simple game that basically allows you to draw different drawings, and your machine learning model is recognizing what you have drawn on a screen. So I'm not very good at drawing here, but what I did, I took this data collected by QuickDraw. So QuickDraw, they have around 300 different drawings, and they collected a lot of data, around 100,000 examples per drawing. I just took 10 classes, alarm clock and asparagus, dolphin. I just took these 10 classes and I trained my own neural network in PyTorch. You can see that it has 2 convolution layers, 3 dense layers, and that's basically it. I just run it for 10 minutes or 20 minutes, and after I think it was 65 epochs, I got this result. So I exported my model as Onyx, imported this into my project, and you can see that Barracuda, this package, allows us to see exactly what kind of layers you have in your model. So you can see that there is 2 convolutions, 2 poolings, flatten, 3 dense layers, and softmax as an output. So I can now use this model together with this inference engine and evaluate whatever inputs I have here in Unity. So on the left side here, you can see that I have 10 results. So this was my output from the softmax layer. It's basically trying to estimate how likely it's going to be alarm clock and asparagus and so on. Here I'm checking the evaluation on my test set, and you can see on the left it gives quite accurate estimations on what is drawn on the screen. I also added this feature that you can try to paint yourself. It's very pixelated. This is because the original data that was collected in a quick draw, it's very pixelated too. So I try to replicate the exact look of the original test data that was provided with the quick draw. Here I try to draw dolphin. A broom, and it's performing as expected, because it was trained with PyTorch. I got into I think 93% accuracy, So this was pretty good, and it reflects what I draw here in the editor. So my estimations are correct. Let's take a look in a script how this is done. So I created this class called Barracuda worker, and this basically grabs the model that I trained together with the factory type, the worker factory type. So this would be instantiated there, and here inside the coroutine, I don't want to stall the main thread, so I did this in the enumerator. Here I'm basically creating a new tensor and assigning inputs based on my texture. Then I pick the output to get my output tensor and then output the results. Recently we added support for the textures and input, so we don't have to assign manually pixel by pixel. All these values can be passed together as a texture. And here I get the result after the softmax, after the entire model is evaluated. I have this 10-dimensional array with the results. If you want to convert PyTorch to Onyx and import to Unity, I tried the torch.onyx export, and this worked pretty well for me. But if you really want to grab any pre-trained model from either Keras, TensorFlow, you can go to our Barracuda package manual, and it will have all the necessary information with scripts. So we provide some scripts. If you use TensorFlow 1, you can use the freeze graph. If you use TensorFlow 2, you can use convert to constraints. There's an example with Keras. So you can check out the documentation and see how this can be done. And this is some useful links that I want to share with you. Here's the Barracuda package link and the example I just showed you on the screen with evaluating the drawing model. If you can't get it, please text me in the Q&A. But it should be public. It's also a GitHub repository. All right, it's time for the Q&A. So could I use this to add to 3D Game Kit on the asset store? Sorry, I'm not sure what you mean by this. Yes, the code is available for the Barracuda demo. This is the second link that I displayed on the screen. It's a GitHub repository, and you should be able to grab it. I don't provide the PyTorch script that was used to train the model. I provide the already trained model. But if you're curious how to train this model, maybe you can bring this conversation to Discord and we can discuss it there. Yes, I'm going to upload this to YouTube. What is the Discord? I'm going to display this as a last slide of today. Why we don't want to increase the learning rate too much? So this is really a problem of hyper-tuning, of tuning your hyperparameters, and this is kind of art on its own. And the problem with the very high learning rate is that with each training step, with each learning step, you kind of push your agent in certain direction with his behaviors. So if you push him too much, he might miss the position at where he had very optimal set of actions, and instead of learning, your basically actions will let's say the desired force that we want to add to our agent to keep him above the ground is 10. So if your learning rate is too high, this would oscillate quite a lot. Maybe it will be plus 100, minus 200, and it will never hit the optimal value. So the Barracuda, it's only used to evaluate the models, and the intended use is that when you have maybe some image recognition algorithm that you want to use in Unity. You can just grab your Keras model, your PyTorch model, you can convert them to Onyx, and you can import them into Unity. Could we do models that process audio with Barracuda? So I've never done audio processing, and I'm not sure what's the size of the input. And I'm not sure exactly, I guess this would be some sort of recurrent neural network, maybe LSTM, something like this. On Barracuda manual page, there is actually a list of supported features. So you can see if your machine learning model supports these features, and then you can try to bring it into Unity. Yes, if you can export Onyx, it should be fine. All right, so here I just want to show you the links I shown before. This is the landing page for the machine learning agent and the link to GitHub. On GitHub, you can find the machine learning agents package together with the manual and documentation. Now, the next webinar in a series is going to be about dots. I know many people are very excited about it. So on the 5th of June, I'm going to talk about dots, which is ECS, job system, and how you can optimize your CPU performance, and how you can create this very large-scale simulations. With dots, you can actually get some really cool results with many thousands of objects moving together. So if you are interested in that, please do register for the next webinar. And please, if you have time, please fill in the survey. This will help me a lot to improve the series. If you have any suggestions in which direction we should go, I'm still experimenting with the format of the webinar. So if you have any suggestions, please do let me know in the survey. I will be really grateful for that. And this is the Discord link. So this is it for today. And if you have any more questions, please join us on Discord, where I can answer some of your questions. All right. Thank you very much for today, and see you hopefully at the next webinar.